We talked about the model of the atom, right? We talked about how in ancient Greece we had our 4 elements is what they thought it was, and then when we got to Dalton in the 1800s, right, he proposed that the atom was this solid, indivisible object. And then, like from the video you watched for your warm-up with J.J. Thomson, we discovered the electron and realized, wait, it's not just one solid thing, but there is at least one type of particle in there, those little negative electrons, as you drew in the plum pudding model, okay? So our next person in history, if you kind of look at the timeline, is we're going to 1910. So not too much longer after J.J. Thomson, we have a scientist named Ernest Rutherford who did what was known as the gold foil experiment, okay? If you look in your notes, I have a picture that looks like this one that shows you kind of the basic idea of what was happening in the gold foil experiment, okay? So what he was doing is he was shooting alpha particles, which are teeny, teeny, tiny, we can't see them, particles that are positively charged at a thin piece of gold foil, okay? And then what he had here was a detector that would light up when an alpha particle would hit it. And so what Ernest Rutherford did is that they expected that the particles would pass straight through the atom. So if you think about it, if our atom is like the plum pudding model with little teeny tiny electrons and then just positive space, he proposed that the alpha particles should be able to travel straight through it, which a lot of them did, but then what was really crazy is some of them were deflected, as if they had run into something or collided with something. So think about it for a second here. If these positive things are colliding and then bouncing off, one, they had to hit something very dense, right? And then if they're repelling, that very, very dense thing must also be positive. So if you think about what other part of the atom we discovered here, hopefully you're thinking our nucleus, okay? So Rutherford is given credit for the discovery of the nucleus, and he determined that the nucleus must be positive. Note at this time that we don't know the difference, right, of what's inside the nucleus, but we just have this solid, dense thing in the middle of the atom. Another important thing from Rutherford is that besides that most of the mass must be inside the atom, is the other idea that, well, if a lot of them went right through, Rutherford has brought up the idea that most of the atom must be just empty space. That we now have this dense nucleus in the middle, the little electrons are around it, and then everything else between is just empty space. Okay, so his model of the atom. Okay, so I guess here are our conclusions. That atoms have a nucleus, and that nucleus is positive. It contains most of the mass. In comparison to the atom, it is very, very tiny, right? Like our video talked about, if you imagine a football stadium, the nucleus is only a single marble in the middle, right? It's very, very small in comparison to the rest of the atom. And then everything else in there must be empty space, right? Because most of our alpha particles pass through, but when one of them would hit right on that dense object, they would reflect back. Okay, his model of the atom is known as the nuclear model. So go ahead and draw that in your notes. Once again, notice that it's not to scale. Okay, that this nucleus is way bigger than what it theoretically should be. And then it would probably be a good idea as you're drawing this, right? So these are like our little electrons. This right here is our nucleus. And then label at this, right, is empty space. Okay, so go ahead and draw that on your notes. And then after you draw that, we're going to watch a little video that kind of shows you a simulation again of the gold foil experiment and kind of how another way to visualize it, or actually how it may have looked to them.
tiny, he found the atom was thought to be a blob of positive charge with negative electrons embedded inside it. Now Rutherford set up an experiment to direct a beam of alpha particles, which he knew to be heavy positively charged particles, and we now know to be nuclei of helium atoms, through a very thin gold foil. The brass can in the centre of the picture contains a small americium-241 cylinder producing alpha particles. Most of the particles are absorbed in the brass. There is a small opening producing a beam of alpha particles. They pass through gold foil, which is about 1.5 microns in thickness, and they are then detected by one of the two detectors set up behind the foil. One of the detectors counts particles going straight ahead, which is the majority, and we count a rate of between 1 and 2,000 per second. The second counter, we can move to measure the scattering rate as a function of angle. Now, the experiment that he and his colleagues carried out was very laborious. It involved them sitting for hours in a dark room, holding a tiny fluorescent screen and looking just by eye at the flashes of light on the screen. We've replicated that with modern detector technology. In its current position behind the foil, it will measure one count every few seconds. As Rutherford deduced, most of the gold atom is empty space, so the alpha particle just goes straight through, doesn't see anything, and goes through in a straight line. Occasionally, one of the particles will come close enough to the nucleus of the gold atom that it will be deflected by the electric field from the positive nucleus. If it comes at a glancing blow, it will be deflected through a small angle. If it hits it head on, it will just bounce straight back. And it's fascinating, I think, to them that this was telling us something very important we didn't know about the very deep structure of matter. It shows that the atom had a heavy nucleus with mostly empty space with electrons distributed around it, which is exactly the picture we now have. It was also the start of particle physics. What Rutherford was doing, what we're doing here, is taking a beam of particles, firing them as a target, looking at the way the particles are scattered, and from that deducing what was going on inside the target. And 100 years ahead, we now have the Large Hadron Collider, where we do the same thing. We fire a beam of particles at a target. In that case, the target is another beam coming the other way. We look for the particles being scattered out of that collision process and try to deduce what was going on in the collision from the behavior of the scattered particles. And all that comes from Rutherford's original idea of firing a beam at a target. So in a century, we've come from an apparatus that would fit on the desk, it was at the cutting edge of physics, to the Large Hadron Collider, which is 27 kilometers in circumference. What was happening was that the alpha particles were going through and missing the nucleus, because the nucleus is extremely small, and the atom, by comparison, is very big. So it's almost all empty space. And we had to wait a long time before one of those alpha particles hit the nucleus almost head on and bounce back into our detector.
Okay, so we had Dalton brought us the atom, J.J. Thomson brought the electrons, we now have the nucleus in our atom. So our next person we're going to talk about is Niels Bohr, okay? Because this is where a big thing of our model changed. So you can kind of make a side note at this time that technically we still don't know about the neutrons yet. The nucleus, right, we know is a positive dense thing, but we haven't broken it down yet, okay? So what Niels Bohr did in 1913 is he kind of noticed something, right? Is we know that positive and negative things attract. So if electrons are negative and the nucleus is positive, what prevents them from just falling into the nucleus? Like, why are they not coming together like opposites typically should? So what he did is he proposed this idea that the electrons are located in these orbits around the nucleus. Kind of like planets orbiting the sun. They have a set path that they kind of stay on, is kind of what Bohr theorized. Okay? So with his model, it's known as the planetary model. And what Bohr did is we say that he quantized the atom. What this is referring to is the idea that only certain energies are allowed. Basically, in our model of the atom, according to Bohr, an electron can exist here on this first energy level, and electrons can exist here on this second energy level, but there's no in between. That's what the word quantized is referring to, that there's set discrete energy levels it must exist in. You can think of the analogy of stairs are quantized, right? Because you can step on the first stair, you can step on the second stair, but there's no other options in between. When a slide is not quantized because there's an infinite number of places you can go. Okay, so with his model, the other thing is keep in mind that we still have that idea of empty space, and that the electrons are allowed on the ring, but not in between. Okay, go ahead and first, before we do that one, go ahead and draw Bohr's model in that picture. Another way in which you can draw it is simply just draw the nucleus, right, positively charged, and then you can just draw the rings, right? These right here are, So these right here are known as energy levels, and they're where little electrons exist, like so. So go ahead and draw his model. Okay, and then the one last thing with Bohr is that electrons are allowed to move from one energy level to another if they absorb or emit energy. So if this little electron gets some energy, then it actually can move up or down throughout the orbits. Okay? And what we'll see actually in another chapter, another unit, is that the energy comes from actually specific colors of light. And once again, we'll see that in another unit of doing a lab, and you'll be able to see the different colors that are emitted as electrons jump. Okay, so what I'd like you to do now is on the bottom of your notes, right, you can have about half a page of blank space, okay, is I want you to write down these example problems of how to specifically draw Bohr's model. What are kind of the rules, okay? So here are the steps. You don't need to write this down because it's pretty straightforward, but I'll tell you what I do want you to write down in your notes. Okay, so when drawing Bohr's model, once again, we need to draw the nucleus, indicating the number of neutrons and protons like we've learned 2 times ago, right? Protons are the atomic number, and neutrons come from the mass. Then we need to draw our first energy level, and then we have specific energy level rules that we'll need to follow. Because only so many electrons can fit on each energy level or each orbit. Okay, and then make sure you keep track of how many electrons you've used and fill it all the way up. Okay, so do write this slide down for me. Okay, so these are the rules you have to follow when filling up your energy levels. So level 1, which is the closest to the nucleus, can only hold 2 electrons. Okay, this little ring right here is too small, no more than 2 can fit on it. Okay, second energy level can hold up to 8. It doesn't have to be 8, but that is the maximum it can hold. Third energy level can hold up to 18, and then the fourth can hold up to 32. And that's as big as we'll go right now. Okay? And then keep in mind that you must fill 1 energy level before you go on to the next. So you're going to put 2 on the first, and then once that's full, then you'll go to the second, then to the third, and then to the fourth. So don't go to the next energy level until the prior one is filled. Okay, I'll give you a few seconds to finish writing that down. So do write these rules down on your notes. And then we'll do 2 example problems. Okay, all right, go ahead and write this example down here of this particular isotope for magnesium. So the first thing we want to do is to draw out our nucleus, okay? So if we're drawing here, we're going to keep it simple, and you'll see on your assignment that you can really just label how many protons you have and how many neutrons. You don't need to draw every little individual circle, okay? So if it's magnesium, the bottom number tells me my proton number. And then if you remember neutrons, we subtract the mass number, so the 24, from the proton number. So we actually also have 12 neutrons. Okay, so here's our little nucleus. Next thing we do is we're going to draw our energy levels. It would be a good idea at this point too to figure out how many total electrons I have. Right, so in this case, it's a neutral atom because it doesn't specify the charge. So I'm just going to write off over to the side here that my electrons, I have 12 of them total. Okay? So then we're going to draw our first energy ring. From our rules, we know that we can fit 2 electrons on this ring. Okay? So I'm going to give you 2 options here of how you can draw it for now. Just for simplicity, if you would like, you can draw out 2 little electrons like so. And now next time I'll show you another option. Okay? So I put 2 electrons there, so I'm going to need a second ring. Okay, keeping track of my total, I've used 2 of my 12. Right, so if you want to kind of keep track, I have 10 more electrons. Okay, keep in mind only 8 can fit though on this ring. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I've used 8. So I still have 2 more. So you're going to need to draw your third ring and put 2 electrons there. Okay, and there's our model for Bohr's atom. This one down. First thing we want to do is figure out our protons and our neutrons, so do our nucleus of our atom. Okay, so looking up at the symbol, we know it's chlorine, so we know it has 17 protons. To find the neutron value, we minus the mass number, so the 36 minus 17, which would give us 29. Oh, I mean 19. Okay. So from there, we now have our nucleus. Okay, and what we want to do is to break down how many electrons.
Okay, everyone, so my camera died, so here's how we're going to finish the last example. Okay, so right here, right, so we have our nucleus that we established. So then our next step is to start putting out our electrons. So notice one thing in our formula that we have a -1 charge. So we have 17 protons, but we don't have an equal number of electrons because there's a -1 charge. So hopefully by looking at that, you can identify that we should have 18 electrons total because there should be 1 more negative than we have positives. Okay, so I can put 2 electrons on the first ring. So your second option on your homework assignment and things is if you don't want to draw the little dots, is I am okay if you just write the number of electrons on the ring itself. Either is fine with me. All right, so we put 2 down. So we go to our second ring. Second ring can hold up to 8. I put 8 electrons on that ring. I got to get up to 18 total, so I need a third ring. And I've done 10 total, so I'm going to fit 8. And then our Bohr model is complete. Okay, so just make sure when you're doing the assignment of keeping track how many electrons you put on each, and then it adds up to the total, and that you don't put more than what is allowed on each ring. Okay, also as a part of this unit, you will be building a model of the atom in correlation to particularly Bohr's model. So, for example, the atom that sits on my desk that I pick up and talk about a lot with the wires and the beads, that was a model made by students through this project. So I'll go over this project more when I get back next week, but I just wanted to give you kind of the heads up so you can maybe start thinking of how you want it to be built. I am going to assign the element to you, so don't start on it yet. But yeah, but there's kind of the requirements. So the requirements will be that you need to build a model of some sort, and it needs to, of course, have the correct number of protons, neutrons, and electrons, as well as they need to be located in the correct place. And then along with your model, you'll turn in a half sheet of paper, and that's all I want, a half sheet of paper that has each of these components on it. And that half sheet can be typed up or handwritten is fine too. So, and then there's lots of different ideas you can use for building it in terms of materials and things. So that is up to you. So once again, I'll go over this more next week and assign you your particular element that you will be building, but you can maybe start thinking about it over the weekend. And you should have this rubric in your assignment packet if you want to take a deeper look at it. Okay, what I'd like to do now is if the substitute could actually hand out your homework practice assignment that you're going to be working on for the rest of class. There's a few adaptation that I want to make. So the sub can go ahead and pause the video right now, pass those papers out, and then I'll explain what I want you to change. Okay, so you should all have your homework in front of you. Okay, so on the front side, just a few things. First off, notice that it says atomic mass. That's not the atomic mass. That should say mass number, right? Because we talked about the atomic mass is what is on the periodic table. It's the average of all of them, and we're looking at just one isotope, so it should be the mass number, okay? So just make that note in your head. Second thing is I want you to add on this problem right here that this atom has a +2 charge. And on this problem down here, I want you to add that it has a -2 charge. All the other atoms on here will say are neutral. All right, go ahead and turn to the back side. What I want you to do is that last column that says valence electrons, cross that off and write charge, and then write down all of these numbers accordingly. Oops. So you can practice writing doing atoms that are not always neutral. Okay, you can go ahead and get started on your assignment. Obviously, as always, work with each other, help each other, but don't depend too heavily on your neighbors. Make sure that you do understand it yourself. Make note of any questions that you have, and we'll spend some time at the beginning of class answering those questions. But yep, okay, good luck.